So the plan for this section now would be to take a look at the phase change aspect. And there is a solver that I have developed that augments OpenFOAM, both geometric and algebraic volume of fluid with phase change, plus some other elements that I will talk about. And part of the tutorials of the afternoon are based on this software. Before doing that, one of you asked me about this OpenFOAM solver updated with all the elements to improve surface tension and so on. And I can show you that it's quite simple to get it and install it in the virtual machine. The link to get it, the link that I showed you in the slide, was the archive paper that they submitted, that now is actually published. But at the bottom of my slideshow, there is the link to get the GitHub page of the solver that is called two-phase flow. I can send all these links later in an email. If you click on the link, you find the GitHub repository for it. And it explains also how to install it, even though there is one thing that is missing. Probably they want to see if you are really familiar with GitHub or not. So you can copy-paste the git clone line. You don't need to do it now, but I just want to show you that it's quite simple to do it. And I like to put everything, the new solvers under this folder called solvers in my machine. So OpenFOAM user v2106 solvers. So I'm going to paste the GitHub command here, git clone with the address. This is just downloading the solver. So you see that now we have, under solvers, there is boiling foam public, which is the my boiling solver that I will talk about later. And now there is a new folder called two-phase flow that we just downloaded. Now I'm going to cd into the folder. So these are all the solvers in this new solver of OpenFOAM. And so all the things that you see online here. So for example, within apps, no, not within apps, but within solver, compressible interflow. So these are all the new solvers to calculate, to improve the VOF method. And for example, under SRC, you find surface tension, surface forces, surface force models. And for example, here you can find RDF, which is a reconstructed distance function, height function, so you can click on it. And I think that actually the height function, somewhere there is a comment that this has been copy-pasted from Basilisk. So they copy-pasted the Basilisk library and they've put it into this one. And so this is just to show you that you can find all the elements within the solver, but now I want to compile the solver. I downloaded it, I want to compile it. Now, if you just type /allwmake, you will get some errors because the git clone downloads the installation for the OpenFOAM 1812. It's an older version of OpenFOAM, which is the version over which this solver was developed. There is an update to a newer solver, to the newer version of OpenFOAM, but it's hidden. It's hidden in this cryptic message. The branch OF2106 works with OF2106. But then it doesn't say how to get that branch. What you have to do is simply to do from within the folder where you have downloaded the solver, so from within two-phase flow, the command git checkout OF2106 now is preparing the compilation for OpenFOAM 2106. So at this point, I go /allwmake, and this should compile the solver. It should take about half an hour, 1 hour. I will leave it there while I'm talking about our next topics. We're not going to use it in the tutorial of today, but really, the virtual machine I'm using I downloaded it yesterday from the one I shared with you. So it's a clean virtual machine, and I'm simply installing the solver. So it should be really plug and play to install it and use it. Hoping that I don't get any error at the end of it. So now I want to go back to the phase change part. Someone during the break also asked me, what if I want to have a more complex mesh, importing an STL? Well, this is one of the exercises I have in the tutorial, but I'm not going to cover them today, where I want to study fluid flow over a surface with cylindrical pillars in cross flow. The surface is made in, I think, a CAD software, exported as an STL file, and it's available in the tutorial. The tutorial will show you how to make a two-dimensional simulation starting from this initial three-dimensional surface. Of course, you can also make a three-dimensional simulation if you want, but the tutorial is just about how to essentially get this two-dimensional simulation of fluid flow through these obstacles. So, phase change, I haven't talked too much about why we are working on phase change. Me personally, when I was a postdoc at the PFL, I was in a laboratory that was fully experimental, and they were testing experimentally these micro evaporators that you can see up here. Now, they're a bit tiny in the image, but these were all parallel microchannels that were half a micron thick and half a millimeter thick, 4 millimeter deep. And there are actually more novel geometries where all these microchannels are square, 100 by 100 micron. So they're quite small, and so I've been working a lot with phase change for cooling of electronics, because eventually you use these boiling flows to maintain the CPUs below the threshold temperature. But you can also find at this link cooling using immersion cooling, which is something you may have heard of, where you dip your CPU entirely into a pool of refrigerant, and you have bubbles generated by boiling over the surface. And boiling is a very effective way to cool down a surface. So immersion cooling is one of the potential future techniques to cool down CPUs. And as one of my postdoc was saying, Luca, do you remember Federico Municchi? Yeah. So he was always, because he was my postdoc, and he was saying, so we do simulations to improve cooling of CPUs so that they become faster, and we can do faster simulations so that we can improve. So it was a funny exponential loop of that. Federico was a very clever guy. And Federico Municchi is actually the developer of the solver I'm going to talk about in the next hour. So he is the developer. He is the one who takes care of the GitHub repository for it. So the GitHub repository for it, I can show it to you already now before talking about it. I think I don't have it here. This is absolutely terrible, but GitHub boiling foam public. So we released it open in GitHub. F. Mooney is Federico Municchi, the developer of it. And as any GitHub release for OpenFOAM, we have applications, solvers. I will talk in the next hour about the solver, so I will not now go into the detail of the solver. The solver is a multi-region solver, so it does conjugate heat transfer between fluid and solid, so you can simulate both fluid and solid and the coupling of them at the same time. And we have also this very useful folder called cases, where there are all the tutorials that we have developed. And today I will focus specifically on 3 of them. So this is available online. There should be the link in my slides somewhere. If it's not, I will send it to you. But, like I said, it's already installed in the virtual machine, so you don't need to install it. But if you want to install it in another machine, it's very simple. As any OpenFOAM solver, git clone, download it from GitHub, /allwmake. So it should be quite simple to use it. Okay, so now going back to my slides, where were I? Let's start in a coherent way from the beginning. Okay, so these are just some cinema of some of the simulations I've done in the past. Here we have a typical nucleate boiling of a bubble on a hot surface using a refrigerant fluid. The birth of the bubble is imposed manually, so the bubble is seeded. This is the problem I talked about at the beginning of the past hour. With CFD, we cannot have the nucleation of the bubble. We need to seed it. Once it's seeded, tiny bubble of a few micrometer, then it grows, and from that moment on, everything is supposed to be physical. But the birth of the bubble, you have to put it yourself manually. Top right is a simulation of a bubble nucleating at a corner of a microchannel and getting bigger, getting elongated, and cooling down the surface over which it passes. So we've published a number of papers on the topic on the bottom right, looking at effect of fluids, shape of the channels, and the heat load, and everything. And it's also validated with experiments. And in the GitHub repository, there are all the validation tests that you can run yourself. So, a few general remarks about phase change. We are using, again, the volume of fluid method. So, the slides I'm showing are the general principles to implement phase change in a volume of fluid method. We have volume fraction transport equation. So here I don't have the anti-diffusion term in this equation because I'm just showing the general VOF equation. On the right side now, this is no longer equal to 0. The right-hand side has a source term due to the phase change rate. So this source term will be active only at the interface, and it's the phase change rate from fluid 1 to 2. We will show later how to calculate it. The phase change rate is kilogram per unit area surface, so how much mass of liquid becomes vapor per unit surface of the interface per unit time. Continuity equation, without phase change, the right-hand side would be equal to 0. With phase change, is different from 0. So you have an acceleration of the fluid when it, for example, liquid turns into vapor, you must have an acceleration of the flow. So this is brought in by the right-hand side. Imagine that a kilogram, take water at 100 degrees. The density of water at 100 degrees, the liquid, is about 1,000 kilogram per meter cube, a little bit less. Vapor is 0.6 kilogram per meter cube. So there is about 2,000 ratio of liquid to vapor density ratio. Imagine a kilogram of liquid that needs to become vapor. The volume needs to increase by a factor of 2,000. So this will cause a big acceleration in the vapor once the, let's say, liquid turns into vapor. And this impact of the density ratio is brought in by this difference in the densities. If ρ1 is equal to ρ2, you actually have no acceleration at all. But this is one of the big difficulties when you want to implement phase change. How to ensure that you have a sharp acceleration only in the cells where this acceleration should be, only on the one side of the interface. Momentum equation is not affected by the phase change term. Energy equation, now we have an extra source term here because phase change will cause removal of the latent heat. If you are evaporating, you are removing the latent heat from the fluid. If you are condensing, you need to bring the latent heat in the fluid. So these are all source terms that if we take a standard isothermal VOF method, you need to implement the source terms, you need to implement the energy equation because the source terms will depend on the temperature field. I forgot to say that all the solvers I'm talking about, they are implementing thermally driven phase change. Thermally driven phase change, it means that you need a temperature gradient to cause phase change. So it's mostly for boiling and condensation. If you want to study cavitation, you can still do it with this solver, but you need a few updates because the phase change rate, as I will show you, in our solver is calculated using temperature fields. If you want to do cavitation, for example, then in that case you may need to implement a phase change due to pressure. Where pressure goes below a threshold, you have cavitation. When temperature goes above a certain threshold, you have boiling. So what I'm talking about now is specifically about boiling, even though the architecture of the solver from this slide could still be the same. What will be different is what you input into M prime prime. Now, there are many models many ways to calculate this rate of mass transfer at the interface. These three are the most popular ones. The first one, approach based on thermal equilibrium at the interface. It assumes that the interface stays at the saturation temperature and evaluates the rate of mass transfer based on the Fourier law. So it calculates the rate of mass transfer based on the heat flux you have at the interface. So you need a heat flux to have a mass transfer. So from a numerical point of view, this one has the difficulty that you need to evaluate the gradient on the liquid side of the interface, on the vapor side of the interface. Heat flux is related to the temperature field. I forgot that this is obvious for a mechanical engineer, but not necessarily obvious for others. But the Fourier equation tells you that it'll be something like this. The heat flux is not a divergence, it's a gradient of temperature. So if you use method 1, these heat fluxes need to be calculated on either side of the interface. I don't know if I go into the details, probably not, because I'm keeping this part quite brief, but I have a lot of slides about phase change models, because it is also part of what I'm teaching. Imagine you have a mesh with an interface and you need to calculate your rate of mass transfer here. So you need to calculate the heat flux on the liquid side, on the vapor side. This is typically done by assuming that the interface is at the Tsat. You move orthogonally, let's say that this is liquid, this is vapor. You move orthogonally about 1 grid cell out on the liquid side. You find the temperature in this point, interpolating the neighbors, and you evaluate your heat flux as TL minus Tsat divided by the distance, and you get the heat flux. On the vapor, you do the same thing. You move 1 grid cell, you get TV, so this point here is Tsat. You calculate the heat flux on the vapor side as TV minus Tsat divided by the distance. So you can calculate the heat fluxes in that way, and that would give you method 1. Method 2 is implemented in many commercial solvers, and it doesn't really have any physical background. It simply calculates the rate of phase change proportional to the temperature of the interface, let's say, proportional to temperature of the interface minus Tsat. And it has this R, which is just an empirical constant. And this empirical constant is problem dependent, grid dependent. Because it's empirical, it doesn't have any physical grounds. And people using approach 2, they typically just use some experimental data to tune the value of this empirical constant. So it's used a lot by people using commercial software, but if you want to use OpenFOAM, OpenFOAM has it implemented in some of the solvers. I would say it's mostly used for kind of industrial work because it works okay, it's not perfect, you can make a company happy, you're not going to make a reviewer of the Journal of Fluid Mechanics happy if you use approach 2. Approach 3, which is the approach I am personally using, it comes from the kinetic theory of gases. And it assumes that the temperature at the interface may have a temperature jump, especially if you go to small scales, you can have curvature at the interface or some kind of molecular resistances to phase change that will cause a temperature difference at the interface. And I'm not showing you all the derivation of this expression here, but it starts from a Maxwellian distribution of the velocity of the molecules near the interface. It calculates how that velocity will depend on temperature and pressure on either side of the interface. And at the end of the derivation, with some simplifications, it has this expression here, which calculates the rate of mass transfer, still proportional to the temperature of the interface above saturation, but the constant of proportionality now has a physical meaning, and the physical meaning comes from the kinetic theory of gases. Inside this coefficient H, which has the unit of a heat transfer coefficient, so watt per square meter Kelvin, we have molecular mass, M, universal gas constant, R, density of vapor, latent heat, saturation temperature, and an infamous coefficient called evaporation coefficient. Now, it's a coefficient that has a physical meaning, and when you have a real interface is packed molecules on one side, which is the liquid side, and then molecules start becoming a bit less dense and much less dense. So at a molecular level, this is how an interface looks like. There is no sharp boundary. The evaporation coefficient tells you of all the molecules that reach the interface, how many are actually able to break free and go into the vapor when energetically that's favorable, and how many they remain trapped for internal attractions. So this coefficient gamma is a ratio of how many jump divided by how many can do it, and it has obviously values between 0 and 1, with 0 being no molecule can jump out, so you have 0 evaporation. In fact, m prime prime becomes 0 if you set gamma equal to 0. Gamma equal to 1 is the maximum rate of evaporation possible, but it's not infinite. With gamma equal to 1, you get a prefactor of 2 divided by 2 minus 1, which is 2. So that's assumed to be the maximum rate of evaporation that you can achieve. Now, how do we set gamma? For the analytical test cases, I typically use gamma equal to 1. So in the absence of any specific information, I use gamma equal to 1, and this gives the best agreement with benchmarks. If I have experimental data, I can try to get a bit of a more accurate value of gamma. It will depend on the fluid, it will depend on the saturation pressure. And the problem of gamma is that it comes from molecular principles. It cannot be calculated directly. And measuring it is very difficult because you need to make, for example, an experiment where you have a very thin film. A very thin film, I mean below micrometer size. You need to be able to measure the temperature of the interface. You need to be able to measure the rate of evaporation. That's the way scientists have calculated the value of gamma. There is no way, to measure it directly with an experiment. It's the result of a very indirect measurement. If you take water, people have measured values all the way to 0.001 to 1. 3 orders of magnitude. So that's the difficulty of method 3, let's say. It's supposed to be valid a bit better than method 1 when you go into microscales, because it can incorporate more molecular effects. But the lack of values of gamma remains one of the weak points of this method. So possibly you must have some experiments available to still compare, for example, the growth rate of a bubble that will depend on gamma and set the right value of gamma. I think that if you set a value of gamma equal to 1, the method gives exactly the same result as method number 1. Method number 1 is not implementing this effect here. This effect becomes relevant only when you look at very small scales interfaces. Okay, now I'm not going into more details of the phase change modeling in general, but there is a lot about it, and we're actually writing a review paper about it. We got major revisions. Hopefully we should be able to go through. We'll have a paper about it very soon. Maybe I shouldn't say very soon because this is very bad. As an Italian, I should never say something like that. Touch wood. And let's talk about validation now. What are the validation benchmarks available for phase change models? There are a couple of validation benchmarks that are one-dimensional, so they're very quick to run, and the tutorial of today is based on this. One-dimensional Stefan problem, it considers the motion of a flat interface due to evaporation. So take a wall, bring a layer of vapor next to it at saturation conditions, and liquid on the opposite side at saturation conditions. Now, the wall is going to be heated up at a temperature much larger than saturation. So you can imagine that the heat will go from the wall through the vapor to the interface. The interface is initially at the Tsat, but as heat is coming from the left, the interface will heat up, and the evaporation model will find either a heat flux or a temperature at the interface above saturation. So it will trigger phase change. So in the Stefan problem, the heat comes from the left-hand side, from the wall, and there is an analytical solution for the one-dimensional problem. You take the heat conduction equation in 1D, time-dependent because the interface will move. So as liquid evaporates, the interface will move towards the right. So this is a moving boundary problem. You have the differential equation governing it. Boundary conditions are T wall at the wall, which is a known value, T sat at the interface, which is known. What is not known is the location of the interface that will vary over time. As initial condition, you can put the interface to be located exactly at the wall. And you have an extra condition to drive the motion of the boundary that this comes from energy jump condition at the interface. So this is telling you that the heat flux at the interface on the vapor side has to match the evaporation rate, essentially. UI is the velocity of the interface. So if you know the heat flux, you can calculate the velocity of the interface. The velocity of the interface gives you the motion of the interface. There is an analytical solution, like I said. It gives you a location of the interface that moves to the right as a square root of time. Beta is a constant that depends on the fluid properties and wall temperature. And you have an analytical solution also for the temperature over space and time. You can use this analytical solution for the position of the interface to validate your simulation. So here on the bottom you see a figure where we get exact solution and CFD solution. The tutorial I have prepared for today, if you can run the simulation, there is also Python code at the end that will just do this plot for you. So this is a problem number 1, 1D Stefan problem. 1D sucking interface, well, this is, the configuration looks exactly like Stefan problem. The only difference now is that the wall is at the saturation temperature, so heat does not come from the wall. The liquid is superheated, so the liquid is actually at a temperature above saturation, so now heat is coming from the right. It's the liquid which is above saturation, which means that at the interface you will have a source term that will make the interface move towards the liquid. This is more challenging than Stefan 1 because you will have a thin thermal boundary layer generated at the interface. If you are able to zoom in at the interface, in Stefan problem 2, if this is x and this is t, and let's say this is the location of the interface, let's say that this is T sat and this is T infinite, the temperature at which you set the liquid. So here you have vapor, here you have liquid. The vapor will remain at T sat. At the liquid you will have a thin thermal boundary layer being generated. Too high. This is T infinite. So this thermal boundary layer is actually quite thin, depending on the fluid properties. And if you don't mesh it with enough cells, you get a wrong result, let's say. You get a not converged result. This problem is not there in the Stefan, in problem number 1, because the heat comes from the vapor. There is no boundary layer being generated in that case. So a coarse mesh is enough for problem 1. For problem 2, what we call sucking interface, you need to have a fine enough mesh to capture this boundary layer. So I am not 100% certain that this problem has an analytical solution. The only one I found is a numerical solution for the one-dimensional problem. So this is still the heat conduction equation, which is exactly as the previous one, but the difference is that now we have done a variable replacement using a variable which moves with the interface. And boundary conditions are T sat at the wall, T infinite in the liquid. As initial condition, you put T infinite everywhere. And the initial position of the interface, again, is very close to the wall. You have a normal velocity jump condition and also an energy jump condition to respect. And you can solve this problem numerically, and I think that in the tutorial we have, there is already the numerical solution with a table with the results. So there is already a solution to compare with. If you run the tutorial, it will go all the way until the end, also plotting your solution against the theoretical one. Problem number 3, which can be slightly more complicated because it's at least two-dimensional axis symmetric. Now it's the real growth of a vapor bubble. So you place a vapor bubble in a superheated liquid. Some of you may be familiar with the Rayleigh problem, where you have the inertia-controlled growth of a bubble. So for example, in cavitation, at the very initial steps of cavitation, the bubble grows, and the growth is only limited by the inertia of the fluid that the bubble is trying to displace. And there is an analytical solution for the problem, which is the one derived by Rayleigh, that tells you that the bubble will grow as a linear function of time. That's the initial stage of nucleation, and is called inertia-controlled stage. As you move to later time instants, so if your bubble is big enough already, from the inertia-controlled stage, you transition towards the heat transfer controlled stage. At this point, the bubble is growing more slowly, so the inertia of the liquid to be displaced is no longer a problem because the bubble is growing slowly. Now the limitation is heat. The bubble is big, and to be able to continue growing, it needs to be fed with heat coming from the liquid. And if heat conduction through the liquid is not strong enough, the bubble will not have enough energy to grow. There is an analytical solution for the problem derived by Scriven, and it's based on the diffusion convection one-dimensional equation for temperature along the radial coordinate. And now I'm not going through the details, but the boundary conditions at which it's solved is a certain temperature in the liquid, which is supposed to be at a certain temperature above saturation. At the bubble interface, you have saturation temperature. And as initial condition, you set T infinite everywhere in the liquid. You have a few energy jump conditions to respect. And this problem has an analytical solution, like I said, derived by Scriven. You can find the derivation in the original paper. And here I'm just showing you the final result that tells that the radius of the bubble will grow over time with the square root of time. So to show you the difference, in inertia controlled stage, the radius grows linearly with time. Later time instance, the bubble grows with the square root of time. And the constant of proportionality depends on fluid properties and temperature. Here I have a setup of the simulation. It's a 2D axis symmetrical simulation. It's also in the tutorial folder. You start with, so the horizontal axis is the symmetry axis. Imagine everything revolves around the symmetry axis to make everything spherical. You start with a small spherical bubble at the center. You put a superheated liquid. We input also a thin thermal boundary layer around the liquid in the simulation. So in the simulation, we need to start with this boundary layer here. Otherwise, we don't capture well the following dynamics of the bubble. Because if we start brutally this way, obviously the interface at time step 0 will find an enormous evaporation rate because of this jump. So you would get a growth of the bubble which during the initial time steps is not correct. So in the simulation, we have this thin thermal boundary layer imposed by the solver. And here you see, for example, over time, 3 different test cases with water, 1 refrigerant fluid, another refrigerant fluid. The discrepancies between simulation, which are the boxes, and the lines is just due to the mesh. This is actually a simulation which was done. The results you see here were actually obtained with ANSYS Fluent during my PhD back in 2010. I did my PhD with ANSYS Fluent. Please don't think bad about me because of that. But back at the time, I was very lazy, and I didn't want to use a commercial, an open source code. So I implemented phase change, and actually I implemented the height function in ANSYS Fluent to calculate surface tension back at the time. A horrible task to do with ANSYS Fluent. But these are the validation tests that I did back then. Of course, these have been all repeated with OpenFOAM, and they are in the tutorials I will present today. This is just how the tutorial would look like when you look at the bubble growing. On the top, you see the velocity field with the vectors colored by the velocity magnitude. At the bottom, you see the temperature field. You see everything is superheated in the liquid, and you have the creation of this thermal boundary layer around the interface due to the cooling that the interface operates. Do we have any questions so far? I'm going to go into the details of the solver afterwards.
I have a question. I mean, what's not related to this exactly?
Yeah?
When you were showing these equations for phase change,
Yeah, the initial ones. Yeah.
Where interface is not at a particular saturation temperature, but it could vary.
That's a bit more difficult. For example, a droplet evaporation on a surface.
Yeah, like just.
Yeah. So you are missing something here, which is the external environment. So the model I'm showing you is for, let's say, phase change in a saturated environment, where the liquid is with its own vapor. If you want to do like droplet evaporation, if you want to do droplet evaporation in its own vapor environment, you can do it. Yeah. But if you want to do droplet evaporation in air, then you need to implement also the concentration equation for the vapor in the air, because it will impact your evaporation rate. Yeah, exactly. So it cannot be done with the solver I'm showing you. This is only for evaporation in a saturated environment. It's not too difficult to update the solver. Essentially, the solver I'm showing you, you would only need to make the Tsat dependent on the concentration of, for example, water vapor on the air close to the interface. So this would be the vapor pressure on the liquid, on the vapor side of the interface. But then it will depend on the relative humidity. So you need to solve an equation for the concentration of water vapor in air. It's something we are trying to do. It's not difficult. People have done it. I'm not aware of any available software solver in GitHub, but it's nothing particularly dramatic. The difficulty, as usual, is that you will also need the gradient of concentration at the interface, which gradients at the interface are always a bit tricky to calculate. I think this has been done in Basilisk. In the Basilisk website, when you open it now, there is the droplet evaporation where they've implemented all this.
It's fairly recent, but yeah. It's
Super recent, yeah.
And the other one, we did a nice workshop in the Lorenzo, the Riviage, a couple of weeks ago.
Okay.
In Bloomfield, Christian Dider's Ruparium has been showing similar functionality to evaporating drops.
Interesting. Okay.
Folks are getting there.
Yeah.
My question is about the previous one, related to so the vapor is not the air, right?
Yeah.
So they are different. So if the liquid is evaporated in air, so this produces vapor. And how the vapor and the air mix, because there are no front surface between them.
Yeah.
So is it something mixing model, mixing mode, or
Well, that would be quite straightforward, I think. You would just have a so for vapor, you would need to, so you would have a concentration equation for the water vapor in air. So I think you can, maybe I'm wrong, I don't know if you can see the whiteboard from there, but I would expect you can solve a kind of transport equation for the C would be the concentration of water vapor in air. And then you have the diffusion term here. So I would expect you can solve a transport equation, like convection diffusion equation for the concentration. But then you need to couple it with the...
Yeah, but then it seems that in this model, you assume that velocity of vapor and velocity of air are the same. But actually,
You're right. Yeah, they share...
if you look at
Yeah.
the kettle boiling,
Yeah.
we can see vapor going up,
Yeah.
up, and the air actually going down. So there should be called the two velocity model, or
Could be done, yeah.
so is it possible?
I think it's possible. It's not that simple then, because everything needs to be coupled also with the liquid.
Yeah.
So, yeah, let's say that this works fine as long as they share the same velocity field.
This is why I think it's a velocity different, no? Because when you see the fume of the kettle, when you see actually the drops, so the water vapor you cannot see.
You cannot see.
You cannot see. So this thing that you see that has a different velocity is because they are dropped, right? So that's a different
There
process.
was no suspension of cold. mean, small doses.
Four, at least, for example.
Yeah.
So that's why you see it has a velocity because of the aerosols,
Okay, well, thanks for the discussion. Okay, so I'm going to move forward looking a bit more into the details of the solver we have created. The solver we have is incompressible two-phase WOF with phase change, thermally driven phase change, and conjugate heat transfer. Conjugate heat transfer means it solves fluid and solid coupled. So we have continuity, volume fraction, momentum, energy equation in the fluid, each of them with some source terms on the right, and these are the evaporation source terms. For phase change, we also solve the heat conduction equation in the solid. For phase change, we use method number 3. So, method number 3, I call it Hart and Vondra because Hart and Vondra were the first to publish how to use method number 3 in a finite volume simulation, in a WOF simulation. And, but the equation to calculate the rate of mass transfer is the same I showed you before. And for the WOF advection, so to solve the WOF equation, we have combined the solver both with the algebraic WOF and geometric WOF, so the user can choose which one to use when they run the simulation. You can call each of the two. For surface tension, to try to mitigate the problem with spurious velocities I was talking about, we have a smoothing method, so we smoothen alpha before calculating curvature and normal vector. It's a bit better than the native version of OpenFOAM. We also have a redistribution of the surface tension force, which is biased towards the liquid side of the interface, which is heavier, and therefore, if there are errors, you see them to a less extent. And so this is, let's say, our solver packaged up in one single slide. And I'm going to talk you very quickly about this smoothing of the evaporation source term now, because in principle, the evaporation source term is only on the cells of the interface where you have a gradient of volume fraction different from 0. So only very few cells have evaporation there. But you can imagine that the evaporation rate could be quite high. You may need to have a very large rate of evaporation put in single cells, which may give rise to some numerical instabilities. So Hart and Vondra, they have devised this procedure to redistribute the source term over more cells so that the overall integral is still the same. You still evaporate the same amount of liquid in a time unit, but it distributes it over a layer of cells around the interface to help with numerical stability. So the steps of the smoothing method is that it takes the original source term only at the interface. It solves a diffusion equation for this source term. This is solved at every time step. There is no time derivative here. It's just a steady state diffusion equation. So you get from this starting point to here. So the colors are coding the value of the source divided by the maximum source you had without smoothing. So 0.1 means that the source is now 10% lower than before. But it's now distributed over a number of cells across the interface. And you can tune the rate of diffusion by changing the D, the diffusion constant that enters in the problem. But the diffusion constant does not impact the global rate of evaporation, only locally if it will change it and make it smoother. Then once you have smoothened out the source term, there is a redistribution step in which you generate vapor on the vapor side of the interface. So let's say that instead of having this source term everywhere around the interface, you split it as a generation of vapor on the vapor side, a removal of liquid on the liquid side. So you actually have a source term overall, your rho dot, which is the source term, is split into two components. So this is done only for numerical stability reasons. And some colleagues have also implemented, like I have a colleague who have implemented it in Basilisk for chemically driven phase change. So he has implemented this smoothing procedure to calculate phase change in a bubble, for a bubble growing because of CO2 coming from the gas into the bubble. But I think that the more rigorous people prefer to have, to not to have any smoothing method, because the smoothing method can a bit interfere with your velocity field at the interface. So with the smoothing method, if let's do liquid vapor, and if you have evaporation, so liquid evaporates, the velocities from the liquid to the vapor, they should increase a lot. So if, let's say here you have these velocity vectors, in the vapor you should have very high velocity vector because of the fact that the vapor is much lower in density. Now, with the smoothing method, you would have a layer of cells where you have this increase in velocity. But physically, it shouldn't happen. Physically, you want to have a sharp change in velocity over the interface. So, some people in Basilisk, but also in Paris Simulator, the code developed by Professor Zaleski, they have implemented some specific method to preserve this sharp change in velocities while preserving also stability of the method. People in OpenFOAM, they have not gone in that direction. People using OpenFOAM, they mostly use this smoothing technique, which will smoothen out a little bit this sharp change in velocity. So, up to my experience, I haven't noticed any weird dynamics caused by this smoothing method. We have validated it with some fundamental experiment of single bubble nucleating, and everything seems to behave quite decently even this way. But I just want you to know that there are various methods to let's say, solve this problem of sharpness of the velocity field at the interface. And this is the one we have implemented in our solver. Okay, here is the link. The public repository can be found at this link, which goes online where I showed you before. And in the virtual machine, the solver is located under the user solvers folder, where now I have put also the two-phase flow solver, the one that I downloaded from GitHub. There are tutorials available, and later on, when we do the tutorials, we can just take them from the folder of the solver and put them into the solver that we will create. Now, there are various tutorials available. I'm not going to go through them now, but Stefan problem is the implementation of the problem one I talked about before. Sucking interface is problem number 2. We will go through this slide in the afternoon. Scriven problem is the problem of the evaporating bubble. So these are all for the tutorials, and hopefully we can look at them and just follow the tutorials for later. And these are 3 extra cases that are a bit more complicated, where there is the nucleate boiling of a bubble, flow boiling in a microchannel, and another flow boiling in a microchannel. And just to conclude these slides, here there are a few additional solvers available in OpenFOAM to do phase change. EvapVOF HART was released by the University of Darmstadt. Phase change heat foam, I think by Penn State University. No, interthermal phase change foam by Penn State University. Phase change heat foam by, I don't know Nima, where he was working back at the time. But you see that the first three are old. OpenFOAM version 2 point something, we are talking about 10 years ago. Two-phase flow is the one I'm installing now in the virtual machine. And there are also other open source software packages for multi-phase flow simulations. Now, this is a bit outdated because I have Basilisk, but I write here, I'm not aware of any phase change solver so far. Well, there is one now, like Radu said. Paris Simulator is the solver released by Professor Zaleski. And there is one publication where they show how they implemented phase change. I just don't know if the code is available open source, if the phase change solver is available open source. Otherwise, the code is available to download. Further material reading, this is about my entire slideshow. So it covers OpenFOAM solvers, it covers phase change, it covers much more than what we have talked about today. We have another 20 minutes, so if you have any questions, feel free to ask. Otherwise, I think I can go into the virtual machine and show you how a tutorial folder is made of. Yes?
Question about the previous slide, where is some kind of calculation and
Yeah.
the version. So the question is precisely for the version. So if I would like to install, for example, the second one, not the version 2.0,
It wouldn't compile.
yeah,
Yeah.
without any problem.
No, it would not. It would not compile. You need to have that specific version, unfortunately. These are old. The first three are from like 10 years ago.
But I'm sorry, can I change some code?
It's not that simple because the WOF in OpenFOAM in the past 10 years has changed a lot. So there would be many, many things you need to update. It's not that easy. On the other hand, my solver and two-phase flow solver are the most recent of which I'm aware. So you can try to use them in a newer version of OpenFOAM, like 2406. There will be probably some changes to do, but nothing dramatically.
Okay, so it would be better to have the several versions of OpenFOAM.
In the end, the best would always be to update your solver to the newest distribution. Otherwise, that's why people have different versions of OpenFOAM installed.
But maybe in the newest versions, already these packages installed, no?
No, because these are very old versions. So in the newest versions, they are not porting anymore the previous versions of the solvers.
So they are not interested in these problems in OpenFOAM?
Apparently, they're not. OpenFOAM decided that they're not interested yet in having their own phase change solver. But be aware that there are some phase change solver in OpenFOAM with VOF. So these are inside the OpenFOAM. But they're a bit complicated and they don't have the functions to calculate mass transfer rate that I want, the one I showed you before. They have some more empirical formulations. So a starting point could be to use these ones and maybe only change the functions for the mass transfer, keeping all the rest of the framework. Any other question or comment? So I'm just going to show you a little bit. Going to the tutorial we will run this afternoon. So the solver is compiled with no issues. So if you want to try to install two-phase flow solver in OpenFOAM 2106 in the virtual machine, it should work without any problem. And that's the solver that has all the more accurate method to calculate surface tension. It already has a lot of phase change models inside. So I would say this is really the most powerful solver ever that you can have for OpenFOAM. Otherwise, the tutorial is prepared using my own solver, but for now, I'm going to run. So the plan of the afternoon is to start with a dump break, two-phase flow, adiabatic case. So I'm going to go back to dump break, which is day 3 in my slides. So this is the kind of problem we want to solve now. And what I want to do in the remaining 15 minutes is just to show you the structure of the case folder, which will always be the same in OpenFOAM after that. So I have put my folder, I copied before, you remember cp -r and that very long path, to take the dump break folder here. Maybe I can make this even a bit bigger. So I'm within dump break. Remember always to type OF2106 every time you open a new shell, otherwise Ubuntu will not recognize the command. And there are a couple of ways to run the simulation. The one you would do when you're an expert is /orun, which will do the mesh, run the simulation, do everything for you. You just have to visualize the results. But today, for the tutorial, I will go through the various steps one by one. What I want to show you now is the structure of this folder. So I'm going to go to OpenFOAM user, run OF training, orig. I can probably, can I make it bigger? Okay, leave it. Run, dump break. So I'm going to open the files one by one. So dump break, we have 0.orig, constant, and system. Now 0.orig is the original 0 folder, which will be modified during the process. So I probably have it somewhere in the slides. But the first step to do is to copy the 0.orig into 0. So I'm going to do cp -r 0.orig 0. Because OpenFOAM will modify the 0 folder at some point. 0.orig is not going to touch it. So if I want to restart the simulation, I can simply copy-paste again 0.orig into 0. Now let's start looking at the files. Let's start with what do we have under constant? We have G. Let's take a look at G. G is the gravity vector. So in this case, gravity is acting vertically downward. So you have 0 minus 9.81, 0. Dimensions, leave that. I think it's no longer necessary in the newer versions of OpenFOAM. But those are the SI units, the International System units, that were standing for kilogram, meter, second, temperature, and I don't remember what else did we have there. So these were the units of the force, meter of the acceleration, meter divided by second power 2. But don't worry about it. In the newer versions of OpenFOAM, this is no longer necessary. Transport properties. So we have phases and phases, water and air. These are just names. Now, water will be phase 1. So OpenFOAM will call the transport variable for WOF, we'll call it alpha.water. Not only alpha, OpenFOAM will have alpha.water, which is the alpha we solve for in the WOF method. It will also have alpha.air, but it will not use it because it will be just calculated as 1 minus alpha.water. Here we need to give the properties. Now, in OpenFOAM, you can also have non-Newtonian fluids with complex rheological properties, and you can do so simply by calling a different transport model. And you have to go and look in the libraries for non-Newtonian fluids that OpenFOAM has to know which libraries are available and which properties they require. If the fluid is Newtonian, you have nu. So this is the kinematic viscosity, density. This is always a mistake you do at the beginning with OpenFOAM because nu is the kinematic viscosity, so you always need to remember that it's not the dynamic one. Density for water, or at least for phase 1. Phase 2, nu and rho, and then sigma. Sigma is the surface tension coefficient. So for the first tutorial, the dam break, we don't need to change anything. We will only look at the files. Then under constant, we have turbulence properties. Now, OpenFOAM has also turbulence models inside. You can also do LES. So if you go for simulation type laminar, it will not implement any turbulence model, which is the case we are solving today. Otherwise, you can simply type K epsilon, K omega, and you can then have turbulence models inside. Even though I guess you're aware that typical turbulence models, they are developed for single phase flow. So if you want to do a two-phase flow simulation with the typical Reynolds averaged turbulence models, I'm not really sure if you can get meaningful values of turbulence at the interface. So these are the 3 files under constant. Let's take a look at 0. Like I said before, 0 is where you put your initial conditions. Actually, it doesn't need to be called 0. But if you want OpenFOAM to start at t equal to 0, you need to have a folder named 0 where you put all your initial and boundary conditions. If you want to start your simulation from time 100, you will call this folder 100. Anyway, OpenFOAM will look for a folder named with a number, and that number will be your initial time. So we start from 0. We have 3 files. We have 3 files because interFOAM is solving for alpha, for velocity, and for pressure. So these are the 3 unknowns in the problem. So if we look at alpha, like I said, alpha.water is the primary variable here. We have internal field. This is the initial condition. Initial condition is a domain full of air. So water water volume fraction is 0. Later, with another utility, we will initialize that box. For now, we have an empty domain, because in this file here, we can only initialize a single value of alpha everywhere in the domain. So if you want to initialize a bubble, a droplet, or any other shape, we need to use another utility. Then, these are all the boundary conditions. I will show you later left wall, right wall, lower wall. These are all dictionaries coming from where we set the domain. Actually, let's show that one first, which is maybe more useful. Y system block mesh. So, now this is a bit of a complex domain. If I show you the slides here, you see it's a complex domain which is not just a square, but it's supposed to have an obstacle over which water impacts. So this domain is built with 5 different blocks, each block with a uniform mesh. So to have all these blocks, you need to set multiple vertices. That's the reason why you see so many vertices defined here. If you want to have just a box domain, you just need 8 vertices. In 3D, you have a cube, so 8 vertices are enough to have a domain. Here you have many, just because the different boxes have different meshes. But actually, with the newer versions of OpenFOAM, you don't even need to split it in multiple vertices. You can just have one single block, and then use some sub-dictionaries for the mesh in the different parts. But let's say you have vertices. On the top, you have scale, to scale down or scale up all the vertices locations. Now, because the domain is a bit of a complex domain with 5 elements, with 5 boxes inside, here we have 5 blocks being generated. But if you have a simple domain with only one box, you only need one line. The lines have the order of the vertices, the number of cells along X, along Y, along Z. Simple grading means that 1, 1, 1 means that the mesh is uniform. If you were having simple grading 1, 2, 3, you would have a uniform mesh along X. If you were having 2 in the second number, along the Y direction, your mesh would become increasingly finer with a factor of 2 every time. If I was having 3 on the last number, along Z, your mesh would become increasingly finer 3 times every time, with a factor of 3 cell after cell. So 1, 1, 1 means that along the 3 coordinate direction, the mesh is uniform. In OpenFOAM, every time you see a parenthesis with 3 numbers, typically is a vector with the 3 components. Scrolling down, now this is the region where we define the boundaries. So in this domain, we have a left wall, a right wall, a lower wall. So these are the names I'm giving. They could be any name, these names. Left wall, right wall, lower wall. It's important that you give the right faces to each wall. So if you have a simple domain, you may have only one face for every boundary. But with OpenFOAM, you can also say that, well, you know, left wall, right wall, lower wall, they all will have the same boundary conditions. No slip for velocity, and a volume fraction equal a specific contact angle at the surface. So potentially, I could put all these faces under the same boundary name so that I only have to define their boundary conditions once. Here, the tutorial is taken from the OpenFOAM guide, so it splits it into 3 different boundary names, which means that when we define the boundary conditions, we need to define a boundary condition for each of these names. Or OpenFOAM will complain saying that it doesn't know about the boundary conditions. Now, OpenFOAM works always in 3D. If you want to do a 2D simulation, you simply put 1 along the Z direction, and there will be only one cell along Z direction. Then you also need to tell OpenFOAM, do we have an empty cell? No, we don't have it anymore. So OpenFOAM will know by default that with one cell, we don't need any boundary condition on the front and back faces. Now, what is important to remember is that we need to define all the boundary conditions on left wall, right wall, lower wall, and atmosphere, which is the top wall. So now we can look again at vi0 alpha.water, and you see that there are all the boundary conditions being defined. Alpha zero gradient means essentially a kind of 90 degrees contact angle on the surface. So we have 0 gradient on the left, right, and lower walls. On the atmosphere, I'm not going to go into the details, but this is a boundary condition to allow water to exit. If you are part of the droplet of this dam leaving the domain, OpenFOAM allows this water droplet to exit without messing them up at the boundary. Default faces are the front and back faces. I don't even know if they were defined in block mesh dict. No, they were not even defined, so that shouldn't be necessary. So potentially you can even delete these default faces. OpenFOAM will not complain because it is not looking for a boundary condition in default faces. 0U, it will look exactly the same. So we have boundary conditions on left wall, right wall, lower wall. No slip is already telling OpenFOAM that it needs to input a no slip boundary condition. And then we have atmosphere at the top, this pressure inlet outlet velocity. So OpenFOAM has the typical Neumann and Dirichlet boundary condition that you can apply, but it also has more complex boundary conditions depending on the flow problem. So for fluid flow, it has all these special boundary conditions that, for example, this one here, I think it tries to preserve the total pressure of the flow at the boundary. So it will adjust the velocity at the boundary based on the requirement that the total pressure must be the same. And this is applied on the top wall. P underscore RGH. Remember that OpenFOAM as a main variable uses the pressure minus the hydrostatic pressure. So they are all kind of, so fixed flux pressure are essentially zero gradient conditions for the pressure. So no pressure gradient in the direction normal to the boundary, or sorry, parallel to the boundary. And at the atmosphere, we have this total pressure uniform 0. So it will change the velocity field to make sure that the total pressure is always equal to a constant value. And because the flow is incompressible, you can give 0 to pressure. Pressure is just a reference value. The flow is incompressible, so only the pressure gradients are important. The absolute values are not really important. And if I go to system, I will take only a very quick look to finite volume schemes and solution. So you remember all the schemes I explained you before. So here now you find them. Div schemes, you can specify the divergence scheme for each convective term of your equations. So div rho phi u is the convective term in the momentum equation. Div phi alpha is the convective term in the Voff equation. Div phi rb alpha is the antidiffusion term, which is also convective term. Now, div of this more complex term here, this is the divergence of the shear stress. So it's the viscous term in the momentum equation. Laplacian scheme, interpolation scheme, surface normal gradient schemes. So these are matching all the elements I told you at the beginning of the past hour. So OpenFOAM is expecting to see entries for each of the convective term, temporal term, diffusion terms that you have. And if we look at solution, these are all the settings for the linear system solvers. So there are already solvers pre-selected. The only elements I typically work on are tolerance and relative tolerance, which is when to stop the iterative procedure for the solution. You have it for alpha, you have it for pressure, different setting for pressure because there is this momentum, there is this predictor corrector procedure, and typically we use 3 correctors where you get a guess velocity without pressure field, you update your velocity by calculating your pressure field multiple times. In this case, it's done 3 times within each iteration. It's 1 o'clock. I will take a break here. When we come back, I explain the remaining files and we start working on the tutorials. Thank you.